Welcome to Working Against Gravity examples. So before we get started, just a quick overview of the force due to gravity. So what is the force due to gravity? If we're working in the imperial system, then the force due to gravity is simply the weight. So the force due to gravity, at least close to the Earth, is simply the weight in pounds. If we are working in the metric system, then the force due to gravity, again, close to the Earth, is mass in kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. So again, this is two different things. When we're working in the metric system, we tend to be given the mass, not the weight. So we do have to do a little calculation to figure out the force. If we're working in the imperial system, we're given the force directly. So let's go ahead and just put this into play and see how we can calculate work in various different situations. So in our first example, you are currently laying on a roof, holding one end of a 10-meter chain. You intend to pull the entire chain onto the roof. If the chain has a mass of 2 kilograms spread evenly along the chain, how much work will you exert to pull up the entire chain? So let's first just sort of draw a picture of what we're working with. So essentially, you're at the top of a building, and we have a chain hanging over the side. And our job is to pull that chain over the roof. So at the start, the chain is an entire 10 meters. But as we pull the chain up, less and less of the chain will be hanging over the roof. So note, as you pull the chain, less and less of the chain will be hanging over the roof. And so what that means is that the remaining mass, or the mass of the hanging chain, will get lighter and smaller and smaller and smaller as time passes. So the mass of the hanging chain gets smaller. And furthermore, the therefore the force due to gravity will be getting smaller. So let's go ahead. I'm going to put my axes, sort of my sort of zero mark at the end of the chain when it's hanging 10 meters below. And then X will be the distance between the original location and the new bottom of the chain. So equivalently, X essentially is measuring the amount of chain that has been pulled up. Right? So we'll set X equal to the amount of chain that has been pulled over the roof. Then the remaining mass of the chain would be, we have 10 minus X meters left times our chain was 2 kilograms spread over 10 meters. So we have 2 kilograms spread over 10 meters. Means that we have 0.2 kilograms per meter, essentially. So if we go back down here, our remaining mass, we would have 10 minus X meters times 0.2 or times 0.2 kilograms per meter. Right? So the force at position X, we take the mass and multiply it by 9.8 meters per second squared. So we have 0.2 times 10 minus X times 9.8 will give us our force. From here, we have our equation for force at any given position. We therefore know that our work was given by, we take the definite integral from starting position to end. So the definite integral from x equals 0 to x equals 10 of f of x dx. So we are looking at the definite integral from 0 to 10 of 0.2 times 9.8 would be 1.96. And so we have 1.96 times 10 minus x dx. At this point, and we just have to go ahead and integrate. I need to give myself a little more room. So from here, we wind up getting, we would have 1.96 times the definite integral from 0 to 10 of 10 minus x dx, otherwise known as 1.96 times 10x minus 1/2 x squared, evaluated from 0 to 10. This, of course, is 1.96 times, we would have 100 minus 50. And then from that, we would subtract 0. So we have 1.96 times 50. And that winds up giving us 98, I believe. And then, of course, our units are Newton meters or joules, right? So we have 98 Newton meters or 98 joules. So this is the work required to raise that 10-meter chain that weighed a total of 2 kilograms over a roof. Again, as we pulled the chain up, we had less and less mass remaining to pull. That meant that that force due to gravity was getting smaller and smaller as we pulled our chain over. And so we were looking at each teeny little piece of movement. We had our force times that tiny bit of distance. So this was our work in the case where we were pulling a chain over a roof. Now we are going to do a very similar example, but this time we are adding a bucket of water to the end of the chain. So we plan to raise a bucket of water out of a 10-foot deep well by pulling up the attached rope. So the bucket currently contains 5 gallons of water. As you lift the bucket, the water spills out at a rate of 0.05 gallons per foot. If the rope weighs 0.25 pounds per foot, the bucket weighs 2 pounds when empty, and the water weighs 8.35 pounds per gallon. How much work will it take to pull the bucket out of the well? So we have essentially the same setup as we had before. We have a rope dangling with a bucket attached. And we are pulling the rope sort of out. And so the force due to gravity will only act on the part that we have hanging. So here we are starting with a 10-foot deep well. So we're starting assuming our bucket was 10 feet down below. Once again, I'm going to put my X as the distance between the bottom of the well and where the bucket is currently hanging. Actually, I'm going to do from the bottom of the well to the top of the bucket. We just need to pull the top of the bucket up to the top, right? So essentially, we just need to pull the length of the rope. So here's our X. That means that the remaining distance is, of course, 10 minus X. So we will have that same setup we had previously with regards to the rope. Our rope was 0.25 pounds per foot. And so that means that our remaining rope we are going to be looking at 10 minus X feet. Oops, 10 minus X, not 10 times X. feet times 0.25 pounds per feet. Or in other words, 0.25 times 10 minus x pounds. So this is the weight of the remaining rope. This is the force due to gravity acting on that remaining rope. In addition to this, we will also have our bucket. Our bucket is a constant 2 pounds on its own. And then we have the water in the bucket. So our water in the bucket, we have 8.35 pounds per gallon. We start off with 5 gallons and we lose 0.05 gallons per foot. So we start with 5 gallons. We lose 0.05 gallons per foot. So for every additional x, we lose 0.05 gallons. And so this would be 5 minus 0.05 times x gallons in our bucket. So this means that our weight, or the force due to gravity, would be 5 minus 0.5x gallons times 8.35 pounds per gallon. Or in other words, 8.35 times 5 minus 0. That should have been 0.05, not 0.5. 5 minus 0.05x. So we have 8.35 times 5 minus 0.05x pounds. So again, I should have mentioned earlier, to counteract the force due to gravity, we just need the opposite force, right? So the force needed should be the weight of the bucket plus the weight of the water plus the weight of the rope. So we have the rope weight plus the bucket weight plus our water weight. So the force at any given position is equal to our rope weight was 0.25 times 10 minus x. Plus our bucket weight was simply 2. And then we have plus 8.35 times 5 minus 0.05x for the water weight. So this is our force due to gravity. We will use essentially that same amount of force. Gravity technically would be negative since it's pulling downward. We will use that same force, opposite direction, to pull upwards. So if I simplify this a little bit, this is 2.5 minus 0.25x plus 2 plus 8.35 times 5 would be, what, 41.75? And then we have minus, we would have the same thing but shifted over. So we would have 0.4175 x. Putting this all together, we have 2.5 plus 2 is 4.5 plus 41.5 would be, 41.75 would be 46.25. And then we have minus 0.25x minus 0.4175x would be minus 0.6675x. So this is our force in pounds. So find our work. Again, the formula for work was we took the integral from our starting position, x equals 0, to ending position, x equals 10, right? This is because the rope was 10 feet. Of f of x times dx, right? At any given position, that's the force required at that precise position, multiplied by that little tiny distance that we're moving at that force, and then sum them all up. So again, we are taking the integral from 0 to 10 of 46.25 minus 0.6675x dx. This is 46.25x minus 1/2 of 0.6675x. So that would be minus 0.33375x squared, evaluated from 0 to 10. Plugging in 10, this would be 46.25 times 10, or 462.5, minus 0.33375 times 10 squared, or 0.33375 times 100. So that would be minus 33.375. And then, of course, plugging in 0, we're just subtracting off 0. So finishing off, we have 400 and what would that be? 29.125, assuming I did my arithmetic correctly. And then this is foot-pounds. So the total amount of work required to raise the rope and bucket filled with water, as the bucket slowly loses water and the rope is slowly losing length, is 429.125 foot-pounds. So assuming I did my arithmetic correctly, I was doing all the arithmetic in my head. These are the answers, but the process certainly is there. So again, anytime we have a situation where we're lifting up a rope, pulling a chain, etc., essentially you want to look at the remaining length multiplied by essentially the mass or weight per unit of length. And then also, if we have an object losing weight, figure out the weight at any precise point in time, and go from there. So again, this is how we can go about calculating work, thinking of it as the weight at one given point in time and just slightly moving the object while it has that weight. All right, in the next videos, we will look at some variations of examples for work.